Assume you're a squirrel and you're enjoying how the train switches tracks. Unfortunately, one part of the rail switch is loose. What's the impact of this? When these flexible tracks are positioned like this, the train wheels naturally follow this path. But once they reach the junction, can you spot the big issue? Do you have a design solution for this problem? To solve this intriguing challenge, we first need to remove the flange from one of the rail wheels. Also, let's use a single track. A single track which is getting divided into two. After reaching the junction, which direction will the wheel move? You're right, it's impossible to predict. Now, let's add a flange to the wheel. Can you tell which direction it will turn? Of course, to the right. If you want the wheel to follow the left track instead, simply make the right track a separate piece and bend it like this before the wheel reaches that point. This is the fundamental concept behind track switching. Now let's see how this works in action. When both pairs of tracks are present, the flange is always on the inner side of the wheels. The portion of the track that bends is called the tongue track. Quite a fitting name, right? When the tongue tracks are bent as shown, the train will move on the yellow track. Remember, due to the presence of the flange, the left wheel cannot roll on the light blue track. Due to the same bending, the dark blue tongue is not at all touching the track. A large gap can be observed, so the right wheel will also be able to follow the yellow track on that side without any trouble. Now, let's bend the tongue tracks the opposite way. This time, a gap appears at the orange tongue region, and the train easily switches to the blue track and moves straight. What a simple and effective mechanism! The moving part of the tongue track doesn't need to be so long. You can shorten it by pivoting it like this. We'll explain the benefits of this shorter design toward the end of the video. Using this mechanism, switching works perfectly. However, if you try running your train on these tracks, it will inevitably derail. The problem lies in the crossing. The tongue tracks cross at one point. If the crossing design looks like this, the train will hit the orange tongue and derail. So how can we fix this? To overcome this issue, just provide a gap near this crossing in both the rails. In this new crossing design, whether the train is going through the left or right track, the wheels cross the junction without hitting any track. So in this new design, the train can switch the tracks and also cross the junction without any trouble. Now, here's a small design challenge for you. Watch the rail wheel movement in slow motion at the crossing. You'll notice the wheels drop into the gap. Can you think of a solution? We can overcome this issue just by increasing the length of the tongue rails as shown. They will provide good support to the wheels during the movement over the rail gaps. The design looks almost perfect now, but this design has a major flaw. To find out the important flaw, we metal 3D printed the entire track switching mechanism using the service of JLC 3DP. Using the JLC 3DP service was absolutely fun. What we did was just the CAD modeling. We went to their website and selected that we need metal 3D printing and also specified the material. To replicate the science behind the rail switches, metal 3D printing is the best. The experts from JLC 3DP analyze your 3D models. In case of any issues, they will let you know. Our models got clearance in one go. In metal 3D printing, layers of metal powder are molten with the help of powerful lasers. Once one layer is complete, the machine adds another thin layer of metal powder above it, and the process is repeated. JLC 3DP's metal printing starts at a price as low as $8. They even have to do post-processing of the 3D prints. After 1 week, we received this box from them. The 3D printed metal pieces were heavy. We truly enjoyed assembling them and achieved a perfect rail track switch. Now, let's roll the wheel along the track. Oh, did you notice that? The train is derailing again. Let's watch it in close-up. What's going on here? Let's watch it from the opposite angle. The right wheel is supposed to travel along this track. But unfortunately, the wheel is traveling along the wing rail and derailing. The majority of the tracks use a larger radius for the turn. If the track has a low radius or high deviation, the chance of traveling along the wing rail is minimum. It's clear from this visual. These two pieces, the check rails, are the saviors of the train wheels. The check rails are placed with a fixed gap with the main rails on either side. Even if the wheels try to travel on the wing rail, the check rail will prevent this. This will channel the wheels onto the track properly, and the wheels will easily pass through the intended trajectory. So even during high speeds, the train can change its journey smoothly. In this 3D printed model, the tongue tracks are flexible. Let's enjoy the design of a perfect rail switch mechanism using this model. Now let's understand the importance of a shorter tongue track. This is, in fact, considered a design optimization. Where do you think the maximum stress occurs in switching rails? It's at the toe of the switch and the nose of the crossing. These parts wear out faster and are replaced more frequently than the main rails. That's why the tongue rail is split into two parts. When the switch rail wears out, you only need to replace that section, reducing steel waste and cost. The tongue tracks are operated together using a switching rod. Long ago, this switching rod was controlled manually by an operator called the point man. You might have seen this cute machine in movies. Nowadays, a smart device called a point machine, which is an electromechanical device, does this task. It's quite a powerful machine. You can see a lot of rods connected to this machine, and it has a lot of electrical contacts and gears. Out of these 5 rods, 1 rod is a throw rod. Suppose this is the current position of the tongue rails. If the station master wants to flex it towards the opposite direction, that signal will be received by the electric motor, and it starts to spin. The torque of the motor gets multiplied by these gears, and eventually the throw rod moves. When the tongues touch the opposite track with the help of the indicator rods, the station master gets a signal that the tongue tracks are in the required position. Along with this, did you notice these electric contacts getting closed? When this happens, the last 2 rods, the locking rods, automatically get locked. The purpose is that when the train travels through the junction, we don't want any movement to the tongue tracks. With the help of these 2 rods, they automatically get locked as soon as the tongue reaches the other end. We can easily ensure this. Now it's time to add more complexity and fun to the railway switches. How can you design a 3-way switch? A rail switch which can guide the train to any of these 3 tracks. Here, of course, you have to introduce one more point machine. But since you already understand the core concept of switching, these animations will make it easy to grasp how the train switches between all 3 tracks. One of the most fascinating innovations in rail switching is double slip switch rail. Here, the design challenge is that Train A should have the option to travel along 2 tracks. Similarly, Train B should also have the option to travel along 2 tracks. 2 point machines are needed for the double slip switch design. With the help of simplified point machine connection, the way the DSS achieves all these 4 scenarios are illustrated here. Routine lubrication of switch points, rods, and moving parts are crucial in smooth operation of a railroad switch. They should also ensure that there's a tight contact between the switch point and the stock rail. So far, when we learned about track switching, we focused only on a few pairs of wheels, but it's truly fascinating to watch how a full train with multiple coaches behaves while switching tracks.
Starting from a simple rail switch, we have understood working of even DSS in this video. However, if you activate the logic of rail engineering you further, you can even design a switching network as complex as this. I hope you truly enjoyed the experiment using the metal 3D prints. I was truly amazed by the precision of these metal components produced by JLC 3DP. If you like to transform your engineering dreams into reality, please check out their website. Take care. Bye bye.